It looks like we can start. Kind of missed the mark there. It's a little bit past. Welcome back, everyone. So we're now on week 7, and next week is midterms week. So definitely getting through it, almost at the halfway mark. The big announcement, though, is our second exam is not on midterm week. It just didn't fall nicely on that date. We're going to have our second exam across from midterm week on this week here. So that means on Friday, of this week, that's when I'm going to start posting the exam 2 information and the review problems, just like we did for the very first exam. Pretty much all that's going to happen on midterm week is on the Friday of this week here, I'm going to calculate your quiz averages, your average score on MyLab statistics, put it together with your exam 1 score. You can see your course score here under grades. It's just a separate title that says course score. It changes by the week. And whatever that settles out on Friday, that's going to be your course grade. Friday of that week there. So midterm week just means for us, no big project. It's just a halfway report kind of situation for this class. Other universities have really interesting things they do, like an entire final exam schedule, a 2-hour midterm exam. But ISU, we just treat it as the middle of the semester, nothing too special. Well, other announcements are the due date for quiz 5 has been pushed back by 1 week. Thanks again for mentioning that about the section 5.4. We have one last part of the last example we need to get through. And also, when I looked into MyLab statistics this morning just to see how it was standing, it looked like I forgot to actually post the section for 5.4 on there completely. So sorry about that. If you're one of those students that likes to work ahead, doing the actual 5.4 problems even before we totally finished it, it was not there. It was invisible. Sorry about that. It's now fully published. It's available to work on. I felt like that's a good enough justification to do an extra example in section 5.4, just so that we can kind of tap the brakes a bit in the course, not rush through it while a section had been missing for a few days. But that's my announcements to start us out. Any questions from you all before we get started today? Okay, let's begin then. So it's kind of rough coming back to the last part of the last problem, but we didn't quite get to the last bit there. So here's where we ended on Thursday. We're working through example 3. The context is pretty brief here. It's just talking about in Rochester, New York, for the entire month of December, they have an average snowfall of 21.9 inches with a standard deviation of 6.5 inches. So we looked into related questions of what's the percent they'll experience 10 inches of snowfall or less, between 10 and 20 inches of snowfall. Both of those questions are values of really what's the area under the curve as a percent. So we use normal CDF on both of those parts there. And this is the one that was just the odd one out. It was asking what amount of snowfall describes the 1% of worst cases for the month of December. And we also mentioned that this is not the best question if it was an exam question, because you have to put in your own interpretation, reading the context of what does worst mean. Too much snow is what I would consider worst to be for most people, but some people might argue with that, particularly if you're a snowboarder or skier or something like that. Do you want more snow? So we went with this interpretation. What is the 1% time you would get the most amount of snow? That's probably the better way to form it if it was an exam question. That means we put 1% on the upper tail right here. And if we can solve for the x value, the whole problem is done. So here's how the problem would start off in the calculator. Let's do this first incorrectly because it's really easy to do, especially on the base model of the TI-84 Plus. It's good to know when it comes out just wrong, and this is what the work would look like. Very first thing you punch into the calculator is the second button, and then the vars key to pull up your distributions. We're going down to inverse norm, so go down to option 3, hit enter, and because 1% came up, if you thought put 1% in the calculator, you know for some people's calculator it works. If your calculator looks like my screen, it doesn't. Let's put that in anyways and see what goes wrong. 0.01 for area. The mean is 21.9. The standard deviation is 6.5. And I did see a peek at someone's calculator in class. The more advanced version of this, I think it says TI-84 plus CE edition, something like that. There's an extra little box that says left, middle, right. So I think about half the people in the class might see that, maybe slightly less than half. If you see that, you want to click on right because your area is to the right over here. That's kind of unfortunate, right? This is the one time where the keystrokes that we put in the calculator actually differs a good amount amongst people in the class. This is the one and only time. So if you don't see that, if your calculator looks like this, here's what goes wrong. We gave an area of 0.01, hit enter just to go through the menus, and we get 6.7. So here's where the diagram's helpful. 6.7 doesn't make sense here. This is snowfall, and this is the upper end. Snowfall in inches. We're expecting something at least around 30 inches, maybe 27, but not 6.7 inches. That's starting to sound like somewhere in Utah or something like that. So if this is what happened, then here's the problem with a lot of people's calculators. A lot of people's calculators is only going to use the area to the left. And for everybody, if you just always use the left button right here, an inverse norm, you'd be doing the same exact thing either way. Area to the left is, well, if it's 0.01 here, it'll be 0.99 on the left. So a lot of things kind of happen in this problem. Just for the sake of review, let's walk through all of them. We started with 1%. But that 1% has to be written in as a decimal, so it became a 0.01. Then we dropped it in right there. But to get what goes inside right here, the area to the left, we go 1 minus the 0.01, gave us the 0.99. So that's a lot of little dots to connect all together. So let's try it out again with the 0.99 area to the left. So hit second bars. You can actually just press the number 3 and it'll go right to the third option. That's slightly faster sometimes. Revise area to 0.99. This particular calculator we're looking at will only give the area to the left. And that's a good enough reminder because that can be pretty confusing sometimes. This calculator only gives area to the left. So that's why we put in 0.99, even though the question was 1%. It said 1% worst cases, so that's really area to the right. But then we have to do this rigmarole in our calculator to get the left area. So here it is on the paper trail for the notes, just as a quick reminder on that issue. But with it set up like this, we should get a more reasonable answer. So hit enter all the way through. And we get a lot more than I thought. 37, we're rounding to 1 decimal place. So 37.0 inches. So the answer to this whole question, we wrote down a lot of stuff just to think our way through it. All the homework system MyLab Statistics wants out of this is just the actual snowfall. So the answer would be this. 37.0 inches. It's one of those rare times where boxing out the answer is good to just convey, this is what we were going for. Everything else is just the work to get us there. And with a lot of these problems, I'll write down included graph, whether it's a quiz problem or an exam problem. I wouldn't penalize you if you just skip the graph. I'll just assume you're a really confident student. You knew exactly how this goes and you're confident on the answer. Or maybe you put a graph on scratch paper. You were thinking about it all along the time. But like we mentioned before, if this wasn't an exam situation, it doesn't hurt to put down the graph. If you have the extra time, that's definitely worth doing. And it's our way of grading on partial credit for this kind of problem. So if anything goes wrong, if I just mixed up the 0.01 and the 0.99, we could lose all of the credit. But if I saw this graph, I would probably give substantial partial credit, even if you gave me the wrong number. I know you set it up right, but there's just that one little logical issue there. That way it goes south. But that's the last one of section 5.4. We'll look into one extra example just to get some additional practice. Any other questions on this one so far, folks? Okay, let me save this one up. And now we're here in the notes. Again, it felt like an extra example was worthy on this one. So for the extra example, the context isn't too heavy, but it's just mostly focusing on practicing on the calculator one more time before we move into chapter 6. Chapter 6 is also going to use a calculator, but I think chapter 5 is where it gets decently tricky. There's really two different versions of the problem, one with normal CDF, one with inverse norm. So here's our extra practice just to kind of tie it all together. Again, maybe not the most interesting context in the world, but it says, there's a machine that cuts corks for wine bottles, and it's supposed to operate in such a way that the distribution of the diameter of the corks produced is well approximated by normal distribution. So the normal model is being used here. By that, we're told we have a mean of 3 centimeters, a standard deviation of 0.01 centimeters, and that's the whole write-up of the problem. So imagine you're a quality control inspection person for some machine, for some company that's doing this kind of work. It's important work after all. You're going to be modeling this by first stating the values of the parameters, kind of a redo of what we did before, but sometimes this is the tricky question in an exam or a quiz setting. When it says use correct symbols for each, just a reminder, we really do have to say, for this part, the mean is mu. In other words, mu goes here. The value of mu is 3 centimeters. When it says standard deviation, because we're modeling a population, we'll use the parameter symbol sigma. So the correct symbols go mu is 3 centimeters, sigma 0.1 centimeters. So that's how we're going to model these corks for the wine bottles. And down below, same kind of questions as before. This is how the questions would be formatted as quiz problems or exam questions. Really, the major difference is the order of the questions could be slightly scrambled. And sometimes there might be an extra kind of concepts type of question like this one. We didn't ask a lot of those in our actual lecture notes, so probably not as many as these. But this is more just to see what kind of neat tricks we can do with the normal model after we've computed something. And that's the something in part B. We're told the specifications for the wine bottle corks, as in these corks are useless if it doesn't fall into this range. The specifications are with diameters being between 2.96 and 3.04 centimeters. We want to know what percent of corks produced by this machine have that required diameter. Well, this question is kind of interesting in a way, because if we go 2.96 to 3.04, notice the mean was 3 centimeters. That's 4 standard deviations to the right at 3.04. That's 4 standard deviations to the left at 2.96. The 68 to 95, 99.7 rule already said 99.7% was within 3 standard deviations. So this is going to be a number pretty close to a 100%. Well, to get started, here's what we would do first. It asks for what percent right here. So the first thing we want to organize in our mind is what calculator function we're going to use. This alone tells us normal CDF is being used. So the percent or area you could consider it as under the curve is given by this function. Next thing we need to know is what's going in the calculator. So let's draw this quick normal model. This is n, and that's where they said it can be described by a normal distribution. That's where the n comes into play. The mean is 3 centimeters. Standard deviation is 0.1 centimeters. So there's a normal model with center right at 3. And we want to know the percentage of the curve of the area from 2.96. Again, that's pretty far out there. So we'll try to just draw it in this way. 2.96, 4 standard deviations to the left, and 3.04, 4 standard deviations to the right. Drawing the picture is really helpful because if we get a small number, we'll know there's just no way that's right. We have a huge range that we're looking over. And this will be the inputs into the calculator. This is input 1, the lower bound. This is input 2, upper bound. And it always asks for these two as the last two inputs, the mean and standard deviation. That's where this is actually pretty helpful, writing down the actual symbol, because it'll connect what we're putting into the calculator. The calculator also prints that symbol. Well, that's the organization so far. Any questions at all, folks, to that step? Okay, so fire up the calculator, hit second vars. I must have missed. Try again. Second vars. There we go. That looks a little bit more normal. Either scroll down and hit enter, or just press the number 2 and it'll take you directly where you need to go. Lower is 2.96. Upper is 3.04. Don't forget to update the mean to 3, standard deviation to 0.1. And our calculators should look about like this for this operation. Hitting enter a couple times, and I get something that doesn't quite look right. 0.3108. I must have missed something. Anyone get something radically different, or let me see what I put in there. So I had a mean of 3, standard deviation of 0.1, and you know what? I think I just really misread this problem. When I was looking at the 2.96, I was thinking 3 minus 4 standard deviations, which was 0.1. I'm off by a little bit, right? That's 2.6, not 2.96. I was thinking I was taking 3 minus 4 times 0.01 in that way, 2.96. I thought of that as being an extra zero in there. My whole entire diagram looks like it's completely wrong. Well, this is like the worst case of scenario of including a graph. I think our number is right, but my graph is wrong on this one. Sorry for the confusion with that one. Let me see if I can backtrack this off. So don't let this happen to you. The graph is supposed to help. This is one of those times where the graph was no help at all. Let me take these off carefully. There we go. So here's my graph one more time. So 2.96, if the standard deviation is a 0.01, right in this location would have been 2.9. So I went way too far on the 2.96. I should have really been way over here. 2.96 would be more like that location. Likewise, 3.04 should be out here. That's a number 3. So my lower should be this number. My upper should have been that number, 3.04. We put it in the calculator right, but the numbers didn't quite look right because my graph was extremely exaggerated from what it should have looked like. It should look just like this, maybe even a little bit closer on the 2.96 and the 3.04. So again, the number 0.1 kind of just messed me up. I thought of it as a 0.01, or that would have been 4 standard deviations, but no, that's not too far at all. That's less than a half a standard deviation to the left, less than a half a standard deviation to the right. Does that make sense to folks on what the issue was there with just the graph itself? Okay, just to recheck the numbers, let me go second vars, hit 2 for option 2, and yeah, the numbers were definitely put in right. The mean is 3, standard deviation is 0.1. Hitting enter through all that again gave us this number. It wants a percent, so go times 100. And to 2 decimal places, this would be 31.08%. So answer on this one, 31.08%. So this is one of those problems where if this was on an exam, that would have been highly distressing because we wouldn't want the correct answer to be erased because our work right here was just incorrectly conveyed. So watch out for those kind of weird mistakes. It might be sometimes a good idea thinking if this is a point one and this is a 3, that location would have been 3.1, and that would have helped us get the numbers in the right spots instead of imagining they were clear out there. That was really bad number sense on that one. But any questions at all, folks, getting through that portion there? Okay, this is probably also really bad for the machine. The quality control person would not be happy because if the machine cuts the corks in that specific way, and we're told the wine ball specifications really do call for the measurement speed to be between 2.96 and 3.04 centimeters, the machine is only giving you a usable cork less than 1/3 of the time, 31.808%. So that's no good for this machine. And that means there'll probably be a follow-up question. What percent of the corks produced by this machine are considered defective? Actually, this is one where you could work really hard. Defective means this area to the left of 2.96 and this area to the right of 3.04. But for working in percents, you can just do the following. Take 100% minus 31.08%, and this will give you the answer just as well. So 100 minus 31.08 in the calculator gives us 68.92%. We didn't do many questions like this one in the official notes, but there could be problems kind of like this in MyLab statistics homework, where you could just reason your way through it and just totally skip doing 2 normal model computations and adding the results together. Does that make sense to folks getting that number there?
But if you were to not skip it, right, it would be the upper end 3.04 would be the lower end, and the upper end would be the 1099 deal.
Exactly, yeah.
Opposite.
Yeah, let's take a look at what it would look like. You'd go, just like you said, second vars, then go down to normal CDF again. That would be the lower this time, just like you said, 3.04. There is no upper for talking defective on the upper range. So we would put in a 10 power 99. Values here would all be correct. And then when we hit enter on that, we would get this value, but it's not quite right because that's just this area, right? It's half of it. Thankfully, though, the numbers are symmetric. This is 0.04 to the right of the mean 3. That's 0.04 to the left of the mean. If there wasn't symmetry there, we would actually have to do 2 computations. But because this area is now totally exactly the same as this area, you can go times 2, just double it, then times 100 to convert it to a percent. And we would get the same value, rounded to the same position as well, 68.92%. Definitely a trickier problem, right? So a question like this one is usually follow up to something like this, where you really actually did the work. You find the area in the middle to get the area on the other opposite ends. If you have the area in the middle, it's just always 100% minus your area. Does that make sense to folks so far? Okay, just to convey that in case that is the way you want to think about this one. It works pretty fast too, you might have noticed. It didn't take that long really in the calculator. This was just a way to do it. So the other way would have been going like this. Here's 3.04. Usually it's better to draw the curve and then put the tick marks down just so you can get everything exactly the way you want them, where you want them. So let me try that strategy there. So here's the center at 3. Here's the 3.04. Then you would want all of this area, N3 and 0.1 again. And that would mean this is your input 1 for lower. Input 2 for upper is 10 to the power of 99, so we use no upper bound. This would be input 3, input 4, then multiply by 2. That's how we're going to get the other area on the far left, where it starts at 2.96. And we're trying to get that area there. I mean, there's a third way to do it, right? You could have also used the lower's 10 power, negative 10 power 99, 2.96 is the upper, then get that area, multiply it by 2, and you would have gotten the same value once again. So really 3 different good ways to calculate on this kind of problem. Any questions on either way of doing it? Okay, this method that we use of taking 100% minus a prior answer actually has a pretty good name to it. This comes back in chapter 4 when we're looking into some probability techniques. We're not going to try to spend too much, not chapter 4, chapter 12. We're not going to try to spend too much time in chapter 12 on probability, but just get enough so we can make nice conclusions when we're in chapters 13, 14, 15. So the idea of taking 100% minus this prior value is called the complement rule. The reason it's called the complement rule is there's really 2 parts. There was this part right here. There was this part together with this one. And all the word complement means is the parts that makes up the whole. And the complement rule, if we take this and put it down right inside there, we make up the whole of 100%. So it's like that was a piece that just slots right in. And visually, that's all the complement rule is trying to do each time we use it. So part C was really, in a certain sense, to let us know sometimes we don't have to work super hard on the calculator. There's just a formula that can help us get to the end result. Well, let's try out the last question here, or it looks like there's a couple more. We'll try out 2 more questions here before we move on to the next chapter. So part D says, what cork sizes describes the 1% largest diameters of corks produced by this machine? Include a graph, round to 2 decimal places. This part right here is kind of a giveaway to the problem. When it says 1% largest, this would be the inverse norm function. Before we even throw anything into the inverse norm function, recall we also need to convert it to a percentage. 1% would convert into a 0.01. So that's one number we would be operating on. And I like that it just says largest, so it directly takes us to the right tail of this distribution. So here's our center at 3. This is the normal model, centered at 3 with a mean of 3, standard deviation at 0.1. And we want, because it said largest right here, we'll shade to the right and put a cutoff value somewhere out here. It's kind of exaggerated. That looks like it's maybe 3%, but again, it doesn't have to be perfect. Just try not to be way off like I did on that problem. That's where it could cause some major issues. That looks like it would convey the information pretty decently. The area that goes here is the 0.01. And so really we're using the complement rule a second time when we go to get this area. This area is 1 minus 0.01, giving us a 0.99 in that location there. So we might as well say it. This really is the complement rule a second time. We're doing it this way because the T84 plus the basic model will only use that particular area, the one to the left. So the inputs to the calculator this time are area to the left. So we're selecting the 0.99. Then that's our input 2 and input 3. So here's what it would look like. Hit second bars. We want option 3, inverse norm. Then area, again, there's some options here. On some people's calculator, you can go 0.101 rather. If you go this route, then you're looking at right tail area. You'll have to select the right button right there to point it towards the right tail. But this calculator that I'm using, that is not a possible feature. So I'm forced to use 0.99. If you want to use that, just make sure you're using the left button because that's the left tail area right here in our diagram. Then update the mean to 3, standard deviation to 0.1. And this is what we would get for x. Comes out to 2 decimal places, 3.23 centimeters. Which is, again, probably going to shatter the wine bottle if they try to fit it in. It was only going to work up to 3.04 centimeters for the wine bottle specification. So that's way out of the specification. But we got it, and it's good to be specific that this was the answer on this one, and the answer on this one is 3.23 centimeters. The goal with writing this stuff down is to never have to use a box, but I feel like these problems just has a cloud of information everywhere. So I'll try to make sure I'm always boxing these kind of problems out. Looks like we're about there to the last one. Does that number look all right to folks? Any questions at the moment? Okay, well, last one for the notes. It's asking what percent of corks produced by this machine are larger than 3.7 centimeters. So for that last problem, let's draw the diagram. I guess we should say as well, is this an inverse norm or a normal CDF problem? Anyone see which function we should use?
Number 2 option.
Yeah, absolutely. That'd be our normal CDF. And the giveaway in the wording is right here when it's asking for what percent. So use option 2, normal CDF. If you're really kind of confused on why CDF, I think we've said it before. Let's say it officially right here. C stands for cumulative. D for distribution, referring to the normal distribution or the normal model. F is function. Function just means process or algorithm or method. So cumulative distribution function just means cumulative adding up the area under this distribution, and it's a function that does that job. So it's a really built up acronym, but in probability theory, it comes up a lot. So the calculator also mentions it as well. So this is N 3.1. We're going to a center of 3 centimeters, and the cutoff value is 3.7 centimeters. So we would be, let's see, somewhere about here. Maybe not quite there. That would be 3.1 where I put it, because that's 1 standard deviation to the right. So in mind of what went wrong on the very first problem of these notes, let me try to make it a little bit more accurate. Here's 3.7 centimeters. So this is centimeter diameter. At this stage, we also want to determine, just so we get it all in the calculator just right, which way are we shading from this position? Is it going to be to the left or to the right?
The right.
Yeah, absolutely. Right where it says larger, this means shade right. So the diagram now looks like this. With that shading in place, it tells us everything we need to know. This is input 1, the lower bound. We're shading to the right without stopping whatsoever. So input 2, the upper bound, is going to be 10 to the power 99. Strange number, but just the largest number we can throw in the calculator. That's input 3 and input 4, the last 2 numbers there. So go second, bars like before, either punch 2 or scroll down and hit enter. Lower bound is 3.7. That's the lowest number that cuts off the area. To get 10 power 99, just go 10. The power button is this one right here above the division sign. And just throw in 99 for our largest number. Then last inputs, 3 for mu, 0.1 for sigma. And that's all the information thrown in. Enter on this gives us a value of, hang on, really small number. I think I made that same mistake as from the very first problem in the notes. Let me take a look at this. Let's put it on the next page. When I put 3.7 here, I was thinking, well, it's not quite 1 standard deviation away. But again, that's a problem with the number sense. If I go 3.1, that's 1 standard deviation away. I think I was thinking that number is a 3.07. 3.07 would have been about here, right? So I place a number 3.7, which is a true 3.07. Again, it's not fun when things go wrong, but that's the kind of thing that can happen with these kind of problems. 3.07 is there, but our number is 3.7. Does that make sense to the folks on what the issue was with this one? Our number is right, but again, the diagram is not conveying it right. 3.7 is actually not there at all. It's way, way out to the far right. Let's see if we can fix this and get a better value out. So if we're thinking in terms of the 68, 99, 99.7 rule, again, the main idea with that rule was it's supposed to help us get the picture just right. And then that rule, this would have been a 3.1 because we're adding 0.1 to the 3. 3.2 is over here, but we're going clear over to 3.7. In fact, there's a problem just like this on the homework, so this is a good one to study even closer. Let me kind of exaggerate my diagram to sort of convey where it's going to end up. It's in fact off the page, but we'll just try to put it in as best we can. And in trying to draw this, the curve is actually going towards the x-axis very, very rapidly. In fact, it never touches it, but I'll draw it kind of like this to convey it's super close. And 3.7 is way out there. So my lower is way off on this one. It should have been this one. Here's the lower. The upper is 10 power 99, but it's the shading that goes to the right of 3.7. There's no way to convey that unless we attempt to zoom way in, which would make the notes kind of unreadable at that point. So putting this all back in the calculator, it was in right, but this is what it should look like. Go second bars, option 2. The lower is 3.7, way out here. Upper is 10 power 99. Mu is 3, sigma is 0.1. We're going to round this to 2 decimal places. Again, this does come up in the MyLab Statistics homework. This is a confusing situation. We did everything right, and we get this. 1.2881 E negative 12. Let's grab that as a screenshot. Anyone happen to know what E negative 12 would convey in the calculator here? Turns out this is scientific notation out of nowhere. So let's unpack that. That's kind of a strange answer. The E negative 12 here means the number you're really looking at is 1.2881. I'll just truncate some of the digits off since we definitely don't need all of them. That might be kind of confusing. Let's just put them all in. 2,655. E power negative 12 is the calculator's way of saying times 10 to the power negative 12. Well, in scientific notation, this number would then turn into, and this is important because we have to round to 2 decimal places, right? We don't round here. We have to unpack the scientific notation first. This number would be taking the decimal spot and moving 12 positions to the left. move 12 decimal places left. So let's attempt that. We need a little bit more space. I'm going to put my 1288, 12655 here. And if I put my decimal place here, that's already one position. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 spots to the left. Let me just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think I missed. There's so many zeros. This is actually kind of tricky. Let me try one more time. It was 1.2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow, I was way off. 11, 12. I should have a zero here and a here. Decimal spot there. Let's double check this. This is really hard on the eyes. So one more try. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Still not quite right. I think this is the right position finally. So that's the number that the calculator is trying to give us altogether. But now when you look at this number and you look at the fact that we're going to round to 2 decimal places, that's the second decimal place. So even if we were off by a couple spots on the point there, we wanted to get it just right for the sake of practice. Either way, this is 0.00 rounded to 2 places. Kind of an annoying problem, right? The punchline to all of this is, if this happens in the homework, and I believe there's at least one question where it does, the big takeaway is, if you have e power really large negative value and you're rounding to 2 decimal places, the answer is automatically 0.00. We could just say literally 0, but putting in the 0.00 is just a reminder this has been rounded. These numbers are actually never 0. If we put in 4, if we put in 50, we put in 10 power 99 as our lower, the number isn't 0, but the scientific notation just has a very large negative number right here as a power of 10. So this is the takeaway for this last admittedly confusing question. If you see some values are just way out of line like this one, your answer is essentially 0. And watch out for these in the calculator. It doesn't mean there was an error, it just means the calculator had to use a special way to describe how small it is at this point, scientific notation. Well, we did it, folks. That's the last one for the notes. These ones got weirder and weirder as we went through the notes, but it's good to see just how weird these problems can get as well, I'd say. Any last questions or comments at all getting through this one? Okay, well, we did it, folks. That's the close of chapter 5. Chapter 5 is going to be our big chapter on using a calculator when it comes to exam 2. There's a little bit of calculator work again when we go back to chapter 6, but chapter 6 really is not as bad as the one we just got through. So the idea of chapter 5 is we're looking into one quantitative variable, looking at data and modeling the population based on that one variable. And now chapter 6 is a little bit different. Here, we're going to look at 2 quantitative variables simultaneously. We'll look into things like how are they connected? What are the relationships between them? What is their association? And that's where we're going to deal with calculating correlation. So we'll be doing some correlation coefficient work, and we'll also do some plots on our calculator to help out with the MyLab statistics homework. I'm plotting actual scatter plots as well. Before we start all of that, here's what the notes looks like when we go to the opening. It's weird, it looks like a math problem, but it's got to start off as something like this, because if we're looking into 2 quantitative variables, that means we're going to have now an X variable and a Y variable in our data that we're going to look into. And these will have special names. The X variable is going to be considered the explanatory variable. The y variable, it has a couple names we could give it. We could call it the independent, or excuse me, the dependent variable, but often it's called just the response variable. So y is going to be the response variable. And the context where this would come together is maybe x is, let's think of a good one. Maybe x might be the size of the engine in the car. Y might be the miles per gallon gas it would get. As the engine gets larger and larger in that car, the response, the way your fuel mileage will change, will go lower and lower and lower. So that's the idea of what we're trying to model now. Two variables that might have some kind of relationship, or perhaps no relationship at all, but we're looking to see if there's one that can be found. In a certain sense, we're redoing what we did in chapter 3. In chapter 3, though, the difference was this was two categorical variables. So looking for connections between them meant we were looking into these two-way tables that looked like this. And whether they were related or not meant we were looking into these kinds of graphs. It's actually a lot of work when it comes down to categorical variables like these. When it comes down to two quantitative variables, the graphs are totally different. We're going to look into something called a scatter plot. But really all the scatter plot is us plotting the x data, the explanatory variable, and the y data, the response variable, into an ordinary xy coordinate system. So that's the math part of the problem. And the tie-in with statistics is we're going to call these scatter plots. Well, that's going to be the setup of the situation for the situation in this chapter, as well as in chapter 7 as well. But to make all of our graphs make sense, we have to do this kind of exercise at least once. So the explanatory variable we think of as being the x-axis or the horizontal axis. For the response variable, we think of that one as being the y-axis. Or sometimes we'll just call this the vertical axis. We think of this as a number line, not too different from what we did in chapter 2 when we were doing a dot plot. But in our dot plot, we just had one number line to consider because it was only one variable that we were looking into. Now, two variables, we're not doing anything too remarkably different. We're going to put it down a dot, but now we treat these as coordinates. Here's what the work would look like to plot these all out. We want to plot the following ordered pairs. They're ordered as in the first number goes with x, the second number goes with y. Right here, we treat this as a 0 position. And so where y is 1, up is going to be in the positive direction. So this would be the coordinate 0, 1. Would be that coordinate right there. Then down the line, just kind of rinse and repeat. If it's a -3, we go to 0 on the x-axis, then left 3 units. The second value is 2, so it tells us we have to go up 2. And that means we would be in this position now. So here's the point, -3, 2. Does that make sense to folks so far? I'm plotting these points at the moment. Okay, again, this is a good enough connection. This is probably something everyone's done at some point in an algebra class, but it could have been quite a while for you. So this is a good one to just warm up and work carefully as we go through it. The connection is in section 2.2, where really we were doing just literally that with this data right here. The issue was we just had one axis. So we took all these numbers, they're all positive, so they all went to the right of 0. In our current problem, they could be positive, negative, or 0 themselves. And they also have information to tell us how they change in the vertical direction, the response variable itself. Oh, let me unpin that. So that's the time for what we were doing before. And just for more practice, let's put in the last points. Next one is at 5, 6. So X direction first, 1, 2, 3, 4, 5, 6. Y direction, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, almost out of the scale. And we end up on that spot. Next one is -1, -4. So we're at -1 here, and then -4 would be 1, 2, 3, 4. So another point way down there. Final point is at 0, 2. So here's 0 in the X coordinate, 2 in the Y coordinate. So that would be the point 0, 2. So we had 5 pieces of data. They're now plot points in the XY plane, so just scattered in two-dimensional space. And that's what our data is going to start to look like in this chapter. Any questions about it so far? Okay, it's good when we put this down to say, what are we actually going for? Chapter 6 is us getting started with the scatter plots and something called association and correlation. But this is what chapter 7 is going to be all about. If you were to try to model these data, there's no normal distribution, but that's what we were doing when there was one variable. When there was one variable, we put the data into a histogram and try to put a normal curve to it. Now there's two quantitative variables, and we want to know, how do we model these data? This is what it's going to look like. These points, well, they're kind of scattered away. This point is the odd one out. But if you can draw a line that goes like this, it gets close to a lot of the points on the graph. It misses this one. This one is going to be considered an outlier. But this is what chapter 7 is trying to do. Chapter 7, we'll use the calculator to compute this line, but chapter 7 is modeling the scatter plot data using a line. And other statistics courses, you might not use a line. Maybe you use something that curves, a parabola shape, or something different. And there's lots of different things we can use. But we're just doing the introductory statistics, so we're going to enter concepts on just trying to find the best fitting line. Line doesn't do the best job possible, and the strength of how well it does is going to be the correlation number. If all these points are really, really close to the line, the correlation will be high. But if the points scatter a lot, like in this graph, the correlation will be a little bit lower or getting close to 0. Then finally, like we mentioned before, this one would be considered an outlier. It's an outlier in the sense that most of our information is pretty close to this line right here. This one is not quite an outlier in the sense that it's close to the line itself. So away from the main grouping of data, but it fits the pattern that we're looking into. This one is worse because it is away from the pattern of fitting into this straight line linear relationship. So that's what makes this one an outlier for these particular data. So in a nutshell, this is what both chapter 6 and chapter 7 are all about, looking into handling two variables at once and trying to fit a line to the data. Again, not too different from chapter 5, except the line that we're putting to the data in chapter 5 wasn't a line at all. It was a curve that looked like this. It was just trying to model the histogram. If we're trying to model points, we're using lines instead. So it feels totally different, but that's just because the landscape is different with two variables. So what we'll try to do next is practice this with some actual context, learn the terminology a little bit better, and that's going to be our first official example. So the scatter plot, like we're just looking into, its whole purpose is to show the relationship between two quantitative variables. Much like how these graphs, these segmented bar charts, we're trying to show the relationships and associations between two categorical variables. If you change the type of variables, man, the work looks totally different, right? One categorical variable with a quantitative variable was bar charts. Two categorical variables were those segmented bar charts here. And now we're using scatter plots for two quantitative variables. So in scatter plots, what is the horizontal variable, and what's the vertical variable, X and Y, has specific names, and we have to sometimes determine those in particular problems. On the Y-axis or the vertical axis, we'll often just say the response variable. Or you could also call it the dependent variable. On the X-axis, we'll think of that as the explanatory variable. Explanatory in the sense that it's going to explain how the Y-axis variable changes as the level on X changes. So that's what we were looking at before. The new thing in this example one is now we have context. So these data, full disclosure, they're reasonable, but they are kind of made up data. But it gets us started on a good warm-up problem. So this says in environmental science, so this is people like the geologists and so on, meteorologists. It is a known phenomenon that as you go higher in altitude, the air temperature tends to drop. And this has a legitimate name. This is called the environmental lapse rate. I learned that just today. So higher you go, the colder it gets. Kind of makes sense. If you're way up there in space, you're going to be very cold. And I have a frame of reference for us. In Idaho Falls, we're on average 1,436 meters above sea level. So this is what this fictitious data is saying happened. Let's imagine it did happen. A research team from the University of Wyoming placed 8 temperature sensors at different altitudes in the Teton Range. So they're in the Teton Mountains at different altitudes. And this is what they recorded. They recorded the average afternoon temperature at each location over a period of 30 days. So if we look at just one column going this way, this was the team from Wyoming at an altitude 1,250 above sea level, so pretty close to where we're at. We're slightly higher. And the average temperature in Celsius was 12.5 degrees. They took this average over 30 days for afternoon temperature. So there's the data. Environmental lapse would say the higher you go up in altitude, 2,400 meters on the upper end, the lower the average temperature should be. And we're seeing that already just on the data itself. Well, what we want to do is construct a scatter plot. We'll do this by hand, but this will be kind of something that we do just to get started. We won't do this a lot. It's kind of tedious. Our calculator happens to be pretty good at doing these, so we'll show how to do this in the calculator on the next examples. But before we do a scatter plot, again, we have to decide what is the x-axis, what is the y-axis, which variable corresponds to which. Thinking about the context, we want to know which one is the response variable and which one should be the explanatory variable. Let's think about that. Is the altitude being explained by the temperature, or is the temperature being explained by the altitude? Absolutely. Going by this part of the context, they told us the higher you go, the air temperature tends to drop. So they're saying the second one is the temperature is being explained by the altitude. That makes altitude itself the explanatory variable. Does that make sense to folks so far? Okay, so this altitude is explanatory. So explanatory variable is altitude. And even though it didn't ask for it, let's just put some extra information here. This will be the x-axis information. That means the response variable will be the average temperature. Temperatures are being explained by how high up you are in the Tetons. So this is temperature. I'll just abbreviate it to briefly temperature. And this would be the y-axis, information. And I have to also be honest when we think about this problem. It's unusual to switch the order of these things. Very often, if your information is in column form, your explanatory variable should come first. It'd be weird to change that around. It would be really weird. If your table is arranged in this way, going horizontally, very often your explanatory variable comes first as well. And if you change that order and publish this information, it's just going to confuse the readers. We all have an expectation there. So when I write quiz problems and exam problems, I'm going to keep that the same because I don't want to write a problem that just looks weird on purpose. But this is more for the sake of MyLab Statistics doesn't hesitate to get weird. They might switch it on you there. So be suspicious of MyLab Statistics. For the things that we put in our notes and our quiz problems and exam problems, the thing that comes first is the explanatory variable. Let's mention that just as a comment here. For good formatting, and MyLab Statistics doesn't follow this, but for good formatting, this variable comes first. So there's kind of a dead giveaway there, but that's good. Conventions help our eyes to see what is going on with the data, even without seeing the context sometimes. And this is one of those times. So it looks like we have 9 minutes. That looks like just about enough time to do the scatter plot. We'll make this our last part for the day, and then come back and finish this off on Wednesday. But any questions at the moment with what we've got going on so far? Okay, here's the next thing that's weird about scatter plots. Oftentimes when we do things in math, we put down an XY plane and we always put down the origin. You don't have to do that, even in a math setting. It just seems to happen all the time in an algebra class. In statistics, that is sometimes a nuisance and not helpful at all, because notice our data is pretty far from zero. We're not anywhere near 0, 0 on these data. So what we typically would do for this kind of problem is say, for the X data, let's state a minimum, state a maximum, and we'll contain our data within that window of minimum and maximum. So the minimum was, this is sorted on altitude, so that's easy to see, 300 meters, and the max was 2,400 meters. For the Y data, let's see, the minimum should be on the far right, 4.9. This data is not exactly sorted. It kind of jumps around a little bit. Actually, it looks like it is sorted. It looks like it's decreasing all the way down, just not by the same amount each time. And the max is 18.1. So that's in meters here. This is in degrees Celsius for the other one. So we want a window that just contains this information. So when we go to draw our scatter plot, it's probably going to look something like this. So this position is no longer 0, 0. We want to put in the y-axis information going this way. And actually, let me put in those colors just to be specific. So there's the y-axis in green. Here's the x-axis in blue. So the minimum was 4.9. So we just need to agree on a value. How about 4? That's going to contain the minimum. Minimum for the x-axis was 300, and that seems like a nice round value. But usually you want to put that position a little bit to the right, so our data doesn't necessarily fall in the corner. Usually we want it in the body, off the axes, somewhere in the middle here. So that's where I would put my minimum. If you put your minimum right here, that would have been okay as well. You have to go up to a maximum of 2,400. So we probably don't want to count by hundreds. This problem will end very quickly if we did that. Let's count by either 200s or maybe even 300s on this one. I'll leave it up to you. I'll go by 300s on this. 300, 600, 900, 1,200, 1,500, 1,800, 2,100, and 2,400. My scale isn't perfect. I notice as my numbers got bigger, they seem to stretch out, but that's okay. It doesn't have to be perfectly drawn. So we're starting here at 4. And I think we can go by maybe 2 degrees at a time, should work out on the vertical direction, or 3 degrees should be fine as well. I'll personally go by 2s. So that's 4, 6, 8, 10, 12, 14, 16, 18. Let's go one more so we contain the maximum up to 20 degrees. So far, this is just like doing the dot plot, except we have another axis thrown on going vertically because now there's two quantitative variables. Next thing we should do to totally complete this graphic is give units for each. And this will be extremely helpful when you go to part C and comment on the display we make. We put in the units, it'll kind of tell a story just by eyeballing it. So in the whole horizontal direction, this was meters above sea level, or altitude if you prefer. And then the vertical direction, this was the average temperature Celsius. I'll abbreviate that again to just temperature. And just to be specific, I'll say in Celsius. So we've got it, folks. This is where the data is going to go. All of these numbers are just going to fit in somewhere here. I noticed it took time just to set up the axes and the units. So we'll have to come back to actually plotting these things by hand. I know it's tedious. We'll do it just once on these notes. After we show how to do it by hand, we're going to start letting the calculator do the heavy lifting for us, just so we don't have to do that every single time you see a MyLab statistics problem come up. But any questions at the moment, folks, on putting just down the axes themselves? Yeah. Yeah, that'd be perfectly fine with me as well. I think that would convey pretty much the whole context at the same time. Other questions? Okay, well, this is what we'll come back to next class. Next class, we're also going to use a calculator a lot. And that's what these two documents down below here are. One of them is a one-time setup. The other one is kind of tricky instructions for getting the scatter plot to go. So make sure you have your calculator next time. I think it's one of those things that are tricky once, but once everything is set up, that's going to be kind of like calculating averages and standard deviations and quartiles. It's just tricky to set up the very first time. But have a great night, folks. We'll be back to it on Wednesday. And congratulations on getting through chapter 5. Usually that's kind of a tricky one to get through, I think.
This is.
Yeah, I got that right here.
Probably.
No worries.
You don't get yours, homie.
That'd be great. Everyone's got weird class policies, so you never know. I've heard students or old professors say that their teachers would do things like lock the doors right as class started, and if you didn't make it on time, sorry, that was it for you. But that was back in the days where there was ashtrays at every table.
Remember them days?
Yeah,
Remember when they used to smoke in McDonald's?
yeah, me too, actually. It was crazy. Any questions?
No, just want to give you a heads up.
Yeah.
This day's my birthday, so I'm probably not gonna go on Wednesday.
Oh, awesome.
Depending. If I go Thursday either, so.
Gotcha.
But I'll watch all the YouTube videos like over the weekend.
Sounds good. Well, happy birthday. And you know what? That's good academic ways to do things. Sometimes you have to take a day or even the rest of the week for yourself.
Exactly.
Then you're come back stronger the next week.
Also just kind of a birthday gift to myself, to be like, here's just a day.
That's awesome. Well, take care. Have a fun time.